Hello, my name is Paul Lee.
Hi, my name is Derek Lau.
Hi, my name is Stephen Mo.
I'm Jimmy Huynh, and this is our assistive medical walker. The motivation and purpose of this project was to design and construct a device that can help individuals who often have trouble getting up from a sitting position and getting down from a standing position. This is why we came up with the assisting medical walker, which aids this problem. The walker functions by having a platform that lays on top of the two 4-bar linkages, which acts as support for an individual to distribute their weight on. Once an individual has positioned themselves on the walker, they may press a force sensor to activate the linear actuator to move the 4-bar linkages forward or backwards. As the linkages move forward, it assists the individual from a sitting position into a standing position, and as the linkages move backwards, it assists the individual into a sitting position.
The initial position of the 4-bar mechanism was 45 degrees to help a person who was sitting down. From that initial position, the 4-bar mechanism would lift them up vertically to a 90-degree angle to help them stand up within a time span of 5 seconds. To achieve this, the angular velocity was determined to be 0.157 radians per second.
For the geometric design of the assistive walker, a prototype was made on a scale 1 to 3. The main concern for sizing components was focused on the 4-bar linkage that would rock between starting and end positions. The length of the links were selected based on a previous kinematic design to be 5, 7, and 11.52 inches. Based on this, a construction of a structure was made to attach the 4-bar mechanism. This 3D design resembles the medical walker. The materials needed to make the walker were selected based on price and access to machine shop. This is the list of components we used for the project. Because of timing constraints, I will mention the most important ones. For example, PVC pipes were used for the structure. The links were made of acrylic, elbow pads for connection, as well as 2.5-inch screws. The final 3D design for the project contains all the parts listed in our bill of materials. This image shows the starting position of the 4-bar linkage. This image shows the ending position.
The forces calculated for the mechanism were at the pin joints for each of the links. The external forces acting on the mechanism are the weight of the person, gravity, and the linear actuator. The forces were all calculated using the 3 equations of equilibrium for each individual link. The weight of the person used as a reference was 50 pounds. From our calculations, the highest value of force was determined to be roughly 18 pounds on the pin of the top link.
It was assumed that the most significant points for stress analysis were the tear-out stress at the connections between the top acrylic link and the bolts, and the buckling stress on the supporting acrylic links when they are in the final position at 90 degrees. The acrylic material had a maximum shear stress of 3,265 pounds per square inch. Therefore, for the safety factor regarding tear-out failure, a value of 54.606 was obtained. As for buckling failure, the 5-inch acrylic link had a critical load of 114.07 pounds, and the 7-inch acrylic link had a critical load of 58.103 pounds. As a result, a safety factor value of 4.56 was obtained for the 5-inch link and 2.32 for the 7-inch link. The team originally believed that tear-out failure would be a more significant issue than failure due to buckling, but according to the safety factor calculations, it seems buckling of the 7-inch acrylic link will most likely occur first before any other component.